This video shows a hypothetical audit of a compiled Java web application running on top of a Tomcat server. The application contains a vulnerability that allows the attacker to determine the existence of a user account which is stored in the MySQL database used by the application. The original source code to this application can be found on GitHub. You might be asking yourself, is the user base of a website really that important to keep a secret? Well, it depends. Certainly the users of this site were not very happy to have their account names exposed as a result of a massive hack in July of 2015. Let's take a look at how our application could be leaking this information. Our application is pretty simple. It contains a login page, and that's about it. The problem is that our application login process has been optimized so that if the user does not exist in the database, we don't have to check his password. While this reduces unnecessary work for the server, it does create a timing difference between users that exist in the database and users that don't. Regardless of what password is entered, a user that exists in the database takes longer to validate than a user that does not. An attacker can use this timing information to verify if a user account is present in the database. Let's take a look at how an attacker would do this in practice. First, the attacker makes a simple login attempt. Notice that it fails. Since the attacker was actually recording all of the requests that he sent to the server, he can now replay those requests multiple times, but each request with a slightly different modification. Let's take a look at what that request looks like. We see that the browser sent our email and password inputs along with a session ID to the server. We're going to fix the session ID for all of the requests we're going to send. Since we don't actually care if the password is correct, we're going to leave the password fixed as well. The attacker then loads a list of usernames that he'd like to enumerate and determine if they exist in the database. When we replay our requests, each request will have a different username. Since every request that we sent is an invalid login attempt, we would expect that the length of the server's response is always the same as well. Sorting the requests by the amount of time it took the server to give a response, however, tells a different story. Since it actually takes longer to validate an account that does exist on the server, we can tell that the Obama, admin, and test accounts all exist in the database. Now, let's see what we could do to detect this vulnerability before it becomes an issue. First, we decompile the application into an intermediate representation that we can work with. Quickly browsing the structure of our decompiled output reveals that this is in fact a Tomcat web server application. Having some domain knowledge of Tomcat application lifecycles provides a good starting point to locate the main entry points into the application. Note that these entry points will represent the primary attack surface area of the application, since their inputs are controlled by users and potential attackers. Since Tomcat always names the entry point methods the same, we can statically search for all entry point methods by searching for methods named JSP service. Notice that two of the methods are outside of the application. Introducing the type hierarchy relationships to our results explains why. All of the JSP methods in the application are overriding behaviors in the base class methods provided by the servlet framework. Now that we know where execution starts in our program for each web request, let's start to consider where timing differences could occur in our program. It's common knowledge that most of the time spent in a program is spent inside loops. So let's start with the assumption that loops are expensive and nested loops are even more expensive than non-nested loops. The loop call graph shows methods with loops and the methods that call those methods. Since the loop call graph can be generated on demand, we can use it to check each entry point for looping behaviors that would be found in the program. Here we see at least two of the main entry points of the program contain calls to methods which contain loops. One of the methods that contains a call to loop is in the Authenticate JSP service. Let's bookmark that information and expand the call graph to see the complete picture of what's happening. The call edge from hash to pbkdf2 is colored in yellow because hash calls pbkdf2 from within a loop. We found two service entry points which make calls to methods with loops, and we should probably audit both of them, but let's start auditing the Authenticate JSP service first. We are looking for flows from secret information to conditions that control branches with differential timing. Again, having some domain knowledge can be utilized to help facilitate our audit. In Java servlet applications, HTTP request parameters are accessed with the getParameter method. Our strategy will be to statically follow the flow of data from sensitive input parameters to conditions in the program. If those conditions control a branch with an observable timing difference, we may have a problem. Here, the analyst is following the flow of data from the input parameter for the email forward in the program. Very quickly, the analyst realizes that the value for the email is flowing outside of the program through an SQL statement. If we haven't done any modeling of how an SQL query could work outside of the application with respect to our application, then we need to apply some more domain knowledge to know that the result could come back in the form of a result set and be iterated using the next method. Based on the SQL query that was sent to the database, the result set should be empty or contain at most one result if the email was present in the database. By examining the data flow, we see that the result does flow to a condition variable. Since this result was tainted by a secret, the existence of a user in a database, then any conditions that are tainted by this result value, which also control branches with timing differences, could potentially leak our secret to the world. If we want to consider all the paths that are defined by the branches at this program location, then we could look at a control flow graph, but even for this toy application, the size of the graph can be very large. Instead, we can create a compacted graph we call the event flow graph, which retains only branches that are relevant to a set of selected events. In this case, our events of interest are loops and calls to methods with loops. The result is a significantly smaller graph which retains all of the necessary information we need to solve our analysis. From this event flow graph, we see that the result of the database query for the existence of the email is used as an input to a condition that is guarding a call to some expensive logic that is used for hashing and validating the password. We can also see that this logic is not performed if the user does not exist in the database. We've now found the timing difference we exploited earlier in this video. Thanks for watching.